pleasure to be here. Good afternoon or good morning or good evening as the case may be. It's 9 o'clock in the morning here in Calgary. This is where I reside. I'm sort of on the other side of those buildings between the city and the mountains. And it's not quite as sunny here today as that picture, so it's not a live picture, but it's pretty nice. Let's begin. I'll first just introduce myself a little bit here. This is sort of my infographic, I guess, and what I could call myself a recovering DBA. I've been a DBA pretty much most of my career. I ended up selling a DBA business that I had, and I had to do something else around the time when I actually built my first real-time data vault data warehouse, and that was back about 15 years ago. Worked with Dan on an interesting project that was essentially a real-time system that was built using Oracle Golden Gate, and it was populating about a 4 terabyte HA built system that was keeping track of all of the electricity that was bought and sold in our province in Canada here. Where they deregulated the industry and needed to not only provide ways for which people to buy and sell electricity, but also we worked for the regulator, who was kind of like the SEC would be in a stock exchange type thing. They wanted to do analytics on the things that were happening in the buys and the sells, as well as predicting supply and demand and that kind of thing. So yeah, we built this with about 5 minutes latency SLA, which is something I'll talk about here in a few minutes. The 5 minutes was the business SLA, but we wanted to architect it. We were asked to architect it so that they could drop it down to a 1 minute SLA. And the only way we could do that at the time, with the technology obviously that we had, was Golden Gate and transforming the log scraping that it does into inserts into another target database, and then sort of munching through those in a micro batch style. And I'll explain what I mean by those terms here in a minute. What's happened since then, obviously, is we've got the advent of distributed and massively parallel systems, so that the scalability of these things are dramatically much higher. And I'll go through what some examples of what's happening out there now in this, and this is really what is coming for us. So let's move on then. My outline is this: is basically to start with, I want to confirm that you need the speed, right? And one of the things that I talked about, I did a presentation a couple of years ago at the conference, and some of these slides are repeated and some of them have been updated. But essentially, I think the first step that you want to do is make sure that you understand what you're getting into, and do you need real time or near real time, or what's the need for your speed? If you do that, the first thing you're going to have to look at is, how do you get the data into the data vault, right, at that speed? So there's several different ways of doing that. Spoiler alert, it's now streaming is basically the way to get it in. We also have to get the data out and make sense of it. And what happens when you have data streaming into a data vault in real time, it changes the perspective, and it really is all about time. The timing associated with these things, and the temporal nature of how you can join different things together, and the differences between streams and tables, we'll talk about here for a bit. And then, I want to also include some of the implications for data vault in these things. And I'm pretty bullish on the data vault architecture as still being the choice for this, in cases where you're not doing a on-demand challenged truly real-time system, which is we'll talk about here in a couple of minutes. But what's happening out in the industry now is we have a tremendous demand for data. And this was a study that was done by IDC Global a couple of years ago now, but it was predicting the total amount of data that we're going to be processing over the next few years. And it's not quite Moore's law. It's not doubling every year, but it's doubling every 3 years. If you look at it, I think I can mark this up here. Say, pick a year where it was 60, roughly, or 40 here in 2019. 3 years from that, 1, 2, 3, we're up at 80. So it's doubling, and then it's doubling again up to over 160 zettabytes, which are really something that I can't even understand. But what's driving this demand for data is essentially a couple of things, I think. One is clearly the Internet of Things and the amount of digital exhaust we produce as consumers, and cell phone and machines and everything is being connected. There's so much more data being done. And this data is coming at us and being used by more complex algorithms. People cannot begin to comprehend the amount of data coming in there, but machines can. So machine learning actually needs a lot of data in order to make predictions and do forecasting. So the component that they predicted for real-time analytics is doubling over the next few years. I think between 2017 and 2025, the component that is real-time is going to be roughly doubling. So we have a case where we have machines talking to machines at high rates, which allow us to do more near to real-time analytics. So what we need to do now, I think, is I'm going to go through the steps necessary to understand what it is you're trying to do. And the first step that I always talk about is just confirm that you need real time. So understand, why do you really need real time analytics? And the question that you want to answer is the so that. And this is a business question. And sometimes our technology backgrounds, and I certainly fall into this, as you want to be a hero, you want to be the white knight or black brave knight or whatever that conquers big data and rescues all these things with real time insights. But really, what is the main purpose of doing this in real time? And I think it breaks down into two main areas. You want to identify the business drivers and the benefits. And the business drivers, an example of this would be timeliness. I need that information. I have to make a decision in a very short amount of time, or I may have a benefit of having all the changes to my data so that I can do more rigorous analytics, but I don't have to do that analytics right away. I might be able to just make sure that I have all that data so that when I want to do the analytics, it's available. So there's a couple of different scenarios that you need to think about. And my suggestion for you is to decouple the ingestion of this data and the consumption of that data using separate service level agreements. And the service level agreement for the ingestion of data can be separated from the consumption of that data, because sometimes the consumption of that data in real time is not what the business is looking for. So if you can separate those things, and then each time you have a business case going through, you can analyze what their latency of service level needs to be. And the latency is really how long it is before the event happens in the business before I can analyze it, essentially. And I always give a plug to Doug Laney's book when talking about this stuff. How do you monetize this information and quantify the business value of this information? And he's got some formulas in there that I have a look at. But one of the components of his formula in this case is there's a timeliness associated with that. And if you can get into business benefits of having that data within a minute or within 5 minutes, 15 minutes, an hour, all of those things need to be considered when you go to architect what your solution needs to be. And really what it ends up being is trying to identify the decision timing. And so what decisions need to be made immediately and what decisions need to be made perhaps sometime later, because sometimes the data itself is only useful while that decision is being made. I worked in a real-time system in our railway system here in Canada, and if the data that you're looking at, they have RFID readers on every car, every kilometer throughout the country. But once that event had happened and roughly 10 minutes had passed, the fact that it was there really had no business value at the end of the day. So it's important to understand what your decision timing is so that you can justify and understand your service levels. Now, I did these charts a couple of years ago, and I'll just run through them quickly. It's thinking about the cost of less latency, and I have one of these triangles where latency is one of the components of it that we need to understand. And if we reduce the latency, we're going to affect the cost as well as the quality of the data. So I'll try and walk through that. And this is meant to sort of highlight where we are today. Most companies are in the 24-hour day. They've spent their money. They have the understanding of that. They're using the good old ETL the way we've always done it. Now what happens is we try to crank our latency down, and you'll notice that bag of money changed to a little bit a bigger bag of money, but not significantly. Sometimes you can go 2 or 3 or 4 times as fast simply by rescheduling and orchestrating how things are run and when they're run. So that's not a big deal. But when you start getting below an hour, oftentimes, in the 5 to 15 minute range, the there has to be some potentially some re-engineering done, and certainly some scheduling and making some optimization changes to the way that you do things. Where it gets much more complicated is when you get down to the 1 to 5 minutes, which is really what most people are thinking about when they think about near real time or real time. So we're not going to be waiting an inordinate amount of time. 5 minutes is where we were at that project that I did 15 years ago, and it required an investment. We had to have a lot of robustness in not anymore the software so much. It's more the fleshware, the people to operate this and to develop it and make sure that it's up to date and working. So the gold standard, I guess, is 1 to 8 seconds, which is really in the area of response time. It's actually that's more what people will accept for response time when answering questions and processing data. And in order to do that, 2 years ago, I drew that bag of money as that large. I would say what's happened in the last couple of years is it's gotten a lot easier to do because of the evolution and the entry of more software that helps do that and abstract the complexity of those things. So take a look at that and to understand where you are on that spectrum, because what you need to do is make sure that you set expectations properly. All right, so I need near real time. Now what? Well, I guess set expectations. So an SLA, which is a service level agreement for latency, is now a critical piece. And the second critical piece to that is instrumenting your data and your whole system so that you can report on that SLA. So instrumentation is as simple in the data vault. It's managing when things are processing. What's the process time of all these things? And then being able to report on those things in a time series way so that you know how far behind you are on average. There's going to be blips, obviously, as operational things happen, but you want to have some sort of 85% of the time we're within a certain amount of time. And when that starts to become difficult, then you can go back to your business and say, hey, we've agreed to this service level and we can't keep up anymore because of the volume has increased or some other reasons. We need to go and look at and optimize that architecture. So aligning your architecture is also important. So one of the things you need to do is understand the role of a data warehouse versus a data lake. And I spent some time on this in the original presentation, but I'll just quickly mention that. And hopefully, since we're on a data vault users group, we have a fan base for data warehousing here, which is what data vault really is. I consider it a lightweight schema on write. So at a minimum, with this information, what we have to do with our data is identify what the business keys are and the business key relationships. The rest of it we can sort of work out later on if we want to keep that in semi-structured satellites, and that's perfectly all right. But we need some schema applied to this data as it comes in. If you're not going to do that, then you're going to just dump the data in raw form into something like a data lake, and then generally what happens is that the persistent stage area or landing zone becomes the way where those things intersect. So I drew a picture of this during that presentation. This is sort of a logical architecture associated with it. And, hopefully everybody on the call agrees that our data warehouse is really the raw data vault. So that's the hubs, links, and satellites associated with your raw data so that we have the facts as they were at the time. Now, remember, the facts are coming at us in a very high velocity rate. So I break the architecture down into two areas. Above that line is a streaming platform where we don't have time to write it down and get back to it later. We need to process it immediately, and more of a batch oriented idea. So oftentimes what we can do though is maybe when we're streaming this data, we also want to push it off into our data lake so that we have it around later. Because some of the streaming platforms will eventually, once everybody who's shown interest in this data has used it, or a certain amount of time has elapsed, the streaming platform may throw those messages away, and you may want to persist them in what would be your persistent stage area or a component of your data lake, right? And sometimes we have users who attach to the data lake, they come up with some useful analytics, but they really want to have that coming through into a data warehouse so that we have a curated sort of official version of what is going on within our real-time system. So there's lots of different ways that this can be done. Let me just erase all of that stuff. And the ways that this can be done break down into basically three possible processing paradigms. And this is right from a book that's an excellent book from Martin Kleppman, Designing Data Intensive Applications. And he says, and I agree, there's three paradigms. One is the challenge response paradigm, and that is truly real time. So what you're going to do is you're going to have a business event happen, and then you're going to pass that business event to something, do some analytics, and wait for it to come back before you act. And that's a coupling of those two things. And it requires some sort of two-phase commit is the way to do it in relational systems. There's distributed equivalents to those things, but basically that is your analytics are essentially part of your operational applications, which is really not the pattern that we're talking about with Data Vault. So I'm not going to talk about that one in much. But our friend is batch. Our batch, we've been doing, this is how it was originally designed. It's all the data via periodic set extraction. You may try to orchestrate it so that you're only extracting things that have changed if you can, that kind of stuff. But it's basically all the data for a fixed period. And then the third one, which is the newer, I guess, way to do this is the streaming, which is a continuous function of what's happened in the business. It's event driven, and it's often managed asynchronously. So the business runs completely oblivious to what's happening with this data as it's being pushed into the queues and processed. It's an asynchronous process so that we don't stop our operational business because our data warehouse can't answer a question. And it's really event driven. It's really the core of what is happening in the digital transformation age. In this age, as people are starting to architect things so that we have microservices, that we have connected devices that are all pushing data into our analytics platforms. CDC is a sort of a log scraping way in which I can observe the changes as they happen to my operational relational systems so that I can turn those into different events as they happen. So there's three possible paradigms. I think, let's look at which your ingestion architecture needs. And I've broken it into sort of two main areas. Above this line is our batch, and this is our streaming. And when Data Vault first started, working with Dan and whatnot, it was basically all full batch. It was an extraction of all the data. We managed the comparison so that we only recorded things that had changed in the satellite, but basically we'd end up writing the new data into our targets. To make latency a little less of a problem, what happens eventually is if you have enough data and it's not changing that much, you end up spending too much time processing all this data. So what we do is something I'm calling incremental batch, but it's figuring out a way for us to extract only the data that's changed. So in order to process that, we use the same sort of approaches and load patterns. What we do with that is we'll try and work something called a high water mark, or there's various names for it, but basically where did I get to before the last time that I looked, and then let's process all of the new data only. Some of the paradigms with this are a little bit dangerous because if you're looking at a last modified date timestamp on a table, you're only going to get you'll only get the latest change. So there might have been a bunch of changes since the last time you looked, right? So you're not going to get all the changes, and you're not going to get the deletes. So you really have to think about what you're going to do with the deletes. And we talk about that in the new section in the class at quite length. But what batch can do, an incremental batch can get you easily down to, the 1 hour time frame through scheduling and making sure you're only pulling out. It's kind of like like a trickle feed of data, but it's processed in batch. So that gets us down, and that might be good enough for what your business requires. But if it's not, the next level you're going to have to go down to is a streaming platform. And a streaming platform is essentially a batch of one, a batch size of one. Each event is placed on a message queue and then taken off to that message queue and then processed. And the processing, it turns out, for the data vault is pretty much exactly the same, except there's the one case that I would encourage you to look at is deploy a non-historized link in some of those high-speed transactions. And you can look up what that is, but it's basically a combination of the link and the satellite together, because you're never going to get a revision to that data for that event. So if you think of IoT, you're never going to see a meter reading get amended later on by an IoT device or a transaction that you're getting that is kind of immutable. So this is a batch size of one, which again requires an increase in processing capability and throughput capability, which we have. But even then, sometimes people want to take what the approach they call is a micro batching, which is actually using batching techniques like a high water mark on my stream of data. So only look at my queue every so often and then process those messages and get some benefits of the set-based processing that you get with the data vault load patterns. So those are, basically the four types of ingestion architecture. I'm moving towards discussing more just the pure streaming, but certainly micro batching is a very, very powerful way to do this, where you get all the data and you can also get some of the processing efficiencies of doing that data without having to do it one row at a time or one event at a time. Okay, so what is this streaming thing? Streaming, is really where we're moving towards and where we're going to be, and what that is basically, and I'm just going to check the chat here while I don't know how to check the chat. Okay. It's where event-based systems are, and streaming data can come in from all different kinds of sources, and they're all managed asynchronously by queues. And these queues are used in a publish and subscribe or producer and consumer sort of metaphor. And this has been around for a very long time. We've had pub sub back since the 80s and 90s. It fell down back then because it didn't scale. Now it can scale. It can scale, considerably. In this case, nothing gets missed. So if I have a CDC, streaming flow, I get all of the changes. Every committed change, every delete, every update will be processed through this this approach. The difference between streaming and batch is that order matters, right? It's an ordered set of operations, as opposed to batch is just a group of operations. So what we process this with is something that's called a log abstracted data pipeline. So the data pipelines that we build in a streaming environment are really an abstraction of the log. And I encourage you to look at, there's a book called I Heart Logs by Jay Krebs, who's the CIO or CEO, I think now, of Confluent, who really explains why the log is the appropriate abstraction for this type of thing. In a streaming, we have some mechanics associated with that. It's the queue is usually managed as a key value pair, and this is one of the things that has happened with the advent of big data and distributed systems. Key value pairs are very predominant, and the value is often a semi-structured bunch of data, and the key in many cases is optional. You may just have a stream of bytes, really, but they're discrete and they're managed as an ordered set of a log of what's happened in there. Oftentimes you'll see them as JSON or Avro or XML or maybe even CSV. One of the things that really struck me when I started looking at this is this concept of stream table duality. And I spent some time on that a couple of years ago. And really what that is it says that a stream and a table are structurally and mathematically the same thing. A table is just data at rest. And the aggregation of a stream of updates over time yields a table. And if you think about, if you've done any database administration stuff, if you think about the transaction log as really a stream of changes for a table, and if you start with an empty table and recover that table across over time, when you stop recovering it, that yields that table. So a table is just a stream that's been aggregated over time, and a stream is really data in motion that you, if you observe the changes to a table over time, that can put things back into a stream. So these things can change form, and really the closure property of math works so that SQL can work on these things, and that's what really interests me. And I told a story about I got to use calculus again, which is something my kid was in high school at the time, and she hated calculus. But basically, the state of a table at any time t is essentially just the integration of all of the times of t of all of the events that happened over the t, and the converse is true. You can observe those changes, and you can also produce a stream of data at t. And that this was a concept again in this book. It's really well explained there if you're interested in it. So when I first started looking at this stuff, I thought, man, this is a unification theory of ETL for batch and real time, and I thought it was going to be really cool. The general theory of stream and table relativity, just like the general physics general theory, but it turned out that a guy named Tyler Akaidu had already coined that term and presented that concept. And his concept is really this stream table relativity, is that these pipelines consist of tables, which is data at rest, plus streams, which is data in motion, plus operations. And the operations are really some form of joining or grouping. So you can take a stream and create another stream by a non-grouping element-wise operation. So if I have a stream of data coming in and I just want to insert additional metadata into that and leave it as a stream going out, that's a stream-to-stream operation that you can do. When you want to turn a stream of data, and the best metaphor I can think of is that if you're looking at an actual stream of water or a flow of water, in order to analyze that water, we need to put it to rest so that we can look at it, put it in a glass or a container of some sort. And that's what the grouping operations that a table does. So a grouping operation, usually over time, but there's other things you can do it on, brings that stream to rest, yielding a table. And it turns out for most analytic use cases, we need a table. We need to look at that data. We can't drink from the fire hose. We've got to put it in a glass or a container or something so that we can make sense of it. We can also turn a table into a stream by ungrouping operations or observation, or they call it triggering. It doesn't have to be database triggers, but it's essentially the same thing. It puts that table into motion, yielding a stream. And of course, you can't go from a table to another table, because you can't go from rest back at rest without going through some sort of motion. So those are the different types of operations that you have in streaming, and it's actually ends up being fairly simple. And what they've done is created ways to do that and abstracted it with APIs and SQL to process these things. So streaming has a couple of different models. The I would call the legacy model would be a shared queue with message types on it. So I've got one queue and everybody just dumps into that queue, and then you pull off it and it might tell you what to do. What you have to do for Data Vault, you have to model that message just like it was a table. What are the business keys? What are the business key relationships? Where's the context and what's it context for inside those messages? You might break them out by message type. You might include the message type as part of the identifying element. Depends on your situation. The more popular version of this now is to have multiple queues, and the multiple queues. This is an example of the architecture for Kafka, which is the one that I'm going to be talking about the most here. And Kafka has the concept of brokers and topics. So each topic is in itself the equivalent of a table, essentially, and then you can scale that up, because every component, every box in this system can be scaled to a massively parallel architecture. And so does this really scale? Well, yeah, it can scale. This is a couple years ago. I looked at LinkedIn, Uber, and Pinterest have published what they're doing. LinkedIn did 7 trillion messages a day in 2019. And I, don't know what it is today, but I know it's probably not going to be less, right? None of these things are going down. Uber uses Kafka. Again, 4 trillion messages a day. They have 80,000 topics and many producers and many consumers. Pinterest does 15 megabytes per second of peak traffic. So yeah, it can scale. I mean, there's some cost associated with it. Obviously, these companies, it's their core business, so they've invested in the infrastructure, but it is possible to do. How do you build these pipelines then? A pipeline construction is simply tables are read into streams or events are published as streams. So we start with a stream, and then streams are processed into new streams until some form of grouping operation is hit. And the grouping operation is going to be driven by what I call business rules, which it's going to be your situation. What do you need? Do you need hourly totals, or do you need every minute totals? Do you need running totals for the last 5 minutes? Those kinds of things. But those grouping operations turn a stream into a table. And then you may not be done there. You may continue to do that until you run out of operations, until you're done with what you need to do. Because sometimes we have to take a table and then start looking at it and doing streaming operations on that. So if we're going to use streaming, we have to determine, what our architecture is. I think Kafka is one of the more ubiquitous ones. It scales. It's open source. It's cloud available, but there's other equally capable systems out there as well. So once we've determined our architecture, the next thing we have to do is start reasoning about time semantics, because time semantics become very important when you get down to streaming operations. There's really 2 types of times. There's business timestamps, and then there's meta timestamps. And the business timestamp is when did it actually happen in the business. Hopefully it's included in your message, right? It's the transaction timestamp. It's when it happened in the business. Meta timestamps are things that we add, the system adds, or the data integration layer adds, like something called ingestion time. And that's something that I think in the data vault is something you want to make sure you keep track of, because that's the only thing that you can really preserve is the order in which it was given to you. And that's what the ingestion time is. The process time now becomes when did you process it through the various layers of your architecture. You do want to keep that. That's what our load date timestamp is in the data vault architecture. It's just when did I insert it? When did I insert it here? When did I insert it there? Then I can use that for time analytics and reporting and instrumentation as to how my system is working. So I've got a couple of, I'm going to just start this up, and then I'll start talking about it here if I can figure out how to start it. This is an animation from Tyler Rickadu's website associated with his book. If you're interested in this stuff, it really gives a real clear definition of what the problem might be. And in this case, he's trying to produce a 2-minute point in time summarization of different scores in a gaming system. And you'll see as event time processes across that axis, the processing time follows along afterwards. And in some cases, you've got data that is outside of the event time. It comes in late, and you may or may not need to process that. You may have to update your totals. It depends on your situation. It's a business rule driven kind of thing. Another visual of this is this one here. Oops. And this is the data streaming through the pipeline as raw bytes. You parse it, you take the user scores, and then you're persisting it in a table over time. And in this case, the green line on this animation is what he calls a watermark, and it's a watermark used by the Apache Beam approach as to whether or not how long you're going to wait before you publish that value. And in this case, he didn't wait very long, and then when the 9 came in late, it was tagged as late, as a late value associated with this particular summation. So these are the kind of things you need to look at when processing stream data. And the way you process stream data basically is through a concept called windowing. And windowing is time-based process for streams. There's several types of windows. The most common one is called a tumbling window, and it's a fixed size, and every event falls into one and only one of these tumbling windows. That's essentially batch. If you think about it, it's a periodic fixed set of data where an event only falls into one window. Very common. The other kinds are less common, but we go through some examples in the class of sliding and hopping windows that events can appear in more than one window. So you want to know what's happened for the last 10 minutes, a minute at a time, and then slide that over. Or you're interested in looking at a user experience type thing where you're trying to identify sessions within a log of events where a user has had some inactivity associated with it. Regardless of how you do the windowing, it's determined by business rules. Like, there's no right or wrong here. It's what do you need to do. It goes back to what are you trying to accomplish? What's the so that you can understand what your windowing needs to be, right? And that's the similar exercise we go through when we design pit tables and bridge tables in our business vault associated with that. What's different though with streaming is that I have this concept of a temporal join, and I'm going to introduce this from a presentation at the Kafka Summit last month. Um, Matthias Sachs did a really excellent presentation, but he's talking about temporal joins and the difference between static data and data that's in motion. Input tables are not static in a streaming environment because they're updated all the time. And the results have to be continuously updated with what he calls deterministic semantics, meaning that if I were to recover my system and start over again, I would come up with the same answer. So relational joins everybody understands what a relational join is. Now we have this concept of a temporal join, and it's a deterministic event time semantics over continuously changing inputs. And in order to do that, we need to introduce a couple of new concepts associated with that. The first, which is our tables in a streaming platform, and the streaming platform I'm speaking of specifically here is KSQL DB, which is Kafka's streaming SQL environment, and tables evolve over time. Here's the changelog stream coming in, and we have different versions of the table that can be expressed at different versions of time. And it's similar to a satellite, but it's not quite a satellite because the table itself, at 1411 is just basically the point in time table, a representation of that satellite, if you will. So now I want to be able to join these things together to produce more useful information. I need to think about a table to table stream, table to table join and a stream to table join. And those are relatively straightforward because we have these temporary tables. So I've got a left table in the join and a right table in the join. My result from a table to table join is going to be another table. But basically this is, some of the, if you've worked on, we spent a lot of time doing this in that original environment because we had to create pit tables all along the way to align time. Now we have a concept and a capability of doing that with native SQL, which is kind of cool. It saves a lot of work because this is complicated to do. If you've ever had to do it, it's tough because you've got to align the time stamps and one of the main motivators of pit tables. Data enrichment is a stream to table join. So I want to take a stream and create another stream, but I'm going to enrich that stream with data from a table. And my table is, of course, a changelog table. So it has a point in time as well with it so that I can take my input stream and an input table, and my result is another stream that's been, enhanced or enriched with data from a table. So I want to look up the customer name when I've got an ID or something like that, that's going to join in more information from another object. Still pretty straightforward. You can do that. Where it gets a little goofy is when you've got two sets of things happening independently and you want to join them. over time. And it becomes a little fuzzy because the time is not going to work. It's the inner join does not work because the timestamps are not exactly the same. What you end up having to do is notionally adding some sort of time condition to what it is you're trying to accomplish from both of those streams. So you join them on the key, and then you want to look for events within a certain time frame. And the way you do it in ksql db is, you join within 5 minutes, which is a tremendously long period of time. In Kafka terms, 5 seconds is a reasonable amount of time. 5 minutes is an eternity, but because of the way things gets processed, that's sort of what you need to do. You need to understand the data and make those kind of determinations if you're going to try to keep two streams of data joined into another stream of data. So those are that's the most complex that we'll have to do. And I want to just switch gears here for a minute and now talk about some of the streaming platform options that you have out there. You can certainly do things in the cloud now with all the major cloud providers. Confluent also has a Kafka managed service in the cloud. You can do it on-prem, or you can do it on your own hardware in the cloud using anything with an MQ in it is a queuing type thing. That just manages those messages associated with that. So the storage component is really not a big game changer. No matter what you do, you're probably going to be okay with that. Where it gets a little interesting is the compute component. I think the storage component, obviously, these are the guys using Kafka. It is more or less ubiquitous in the largest use cases, and it's I think the most popular one as well. So let's look at the different options from the compute standpoint, which is where it gets a little bit interesting, I think, because you've got levels of abstraction available to you to make it simpler to deal with all of this data. The lowest level of abstraction is you write to an API or you create customized objects. Right? So Java, Python, Spark, Scala, you can create objects in Snowflake, using Snowpipe to manage that stuff directly. And that's purpose built, absolutely the most flexible, but it also is the lowest level of abstraction. A higher level abstraction are some of the GUIs associated with that sort of make that whole process bundled up and easy to work with. I've worked with stream sets a bit, pretty cool. Informatica, Talent. These are the, maybe some of the former ETL vendors have included additional capabilities so that you can use a familiar, development paradigm associated with that. And then the highest level abstraction, I think, is SQL. And a couple of years ago, I went through examples of Apache Calcite and Horton DataWorks platform. Stream is a new one. We've got a proprietary. They're using Kafka as the guts. They're using open source big data tools at the guts, and they've written a SQL processor. The one that I'm most familiar with is ksql, which is the extension, I guess, or the Confluent Kafka version of SQL on top of a streaming platform. I wanted to also shout out here, if you're interested and you're a Snowflake customer, there's a wonderful post on the Data Vault Alliance on building a real-time Data Vault solution in Snowflake, really well explained and walked through. Snowflake certainly gets you down to the micro batch level perhaps, and that is most likely going to be good enough for you. So I think if you're using Snowflake, I would encourage you to have a look at that post on Data Vault Alliance. How am I doing for time? I've got 10 minutes here. So I've got an example here, and I'm working on a class with Dan to do some hands-on stuff with this, with Kafka, and probably Snowflake is going to be the other one. But here's an example of a hub that's expressed as a stream and as a table, right? And the difference between those two, hopefully you'll get an understanding for it. But the stream, and when you join to the stream, you can get another stream associated with that. And in this case, it's basically the account ID is the business key, and I'm going to partition that stream by my hash key so that I can do my joining. Joining of things in streams are very partition constrained. So there are some constraints in the SQL environment that you need to make sure the data and in your stream topic is oriented properly. If you want to create a table, and what I did with this one is I created a table, and you'll look at that latest by offset. That means that's a current value. That is the absolute value right now of all of the different account IDs, record sources, and ingestion timestamps. And then using Kafka Connect, I can push that into a PostgreSQL rendering of that table and have Kafka manage that as things go through the changes. So it's pretty robust, and it works pretty well. And the good news, I think, is that Data Vault 2 supports robust streaming. I mean, we don't need, one of the problems with real-time systems is this exactly once semantics, which I haven't even explained, but it's not required here. And it's something that because of the way the Data Vault works, we have idempotent, deterministic, isolated load processes that by design won't run into problems that you can run into without those things associated with that. So I think we're in good stead here. What's kind of different, though, I think a little bit, is that the business rules and the business vault, the definitions haven't changed. Soft business rules created information. What's maybe changing a little bit is this notion of time, or some monotonic, which is continually increasing value, that the grouping operations are called. And the windowing has to be determined by business rules. So anytime you've taken your raw data stream and you're starting to group it, you are crossing that line from raw into, in my estimation, business vault territory. Doesn't really matter, but you want to make that distinction, because that is something that might change. The business may come back and say, we said we wanted it windowed in every 5 minutes. Let's go down to 1 minute and see, because we need to get better granularity on the decisions that we need to make. So the business rules are applied via windowing, determines the temporal semantics that you're going to be using. And for the most part, I would recommend that you try to use event semantics on that. In Kafka, you sort of declare whether you're going to be using event time semantics or ingestion time semantics. And you use ingestion time semantics if you don't have an event time in all of your use cases, which hopefully that's not going to be the case. But they're basically soft rules, right? And essentially are subject to change. And what we end up with is these pipelines now are dependent streams and tables in our business vault, and all the way down to our information mart. In my testing, I've also created summary tables and facts and dimensions that are all processed as a continuous pipeline. When one changes in the raw system, it percolates all the way through to the resulting aggregation tables that I'm trying to create facts and dimensions on. It's very similar to pit and bridge concepts, but the objects are created declaratively using SQL, which is kind of interesting. And I think I'm going to sort of wind down here at this point now, and just give a plug to last year we rewrote the certification section on real time. I developed that. We talk about this a lot more in the certification class, so go Performance G2 or through the Data Vault Alliance. You can sign up for that. If you're interested, we're also looking at, I'm working with Dan on a hands-on class for this kind of stuff. So if you have a use case, a couple of years ago I talked about this as more of an experimental, and it would be nice, wouldn't it be nice? I think it's absolutely possible, and I'm willing to be proven wrong on there, but I just haven't got the use case and then the time and money, I guess, to go prove myself right. But I'd love to be proven right on this. But I think it's now, I'm convinced that this can be done. And if you're interested in that, please drop me a line or talk to Dan about what we're doing in that. And with that, I'm going to stop my presentation. That's my email, and I don't know if there were any questions.
Thanks, Bruce. It's been very interesting.